Okay, so last time should have been the last lecture really, right? Because I ended up with talking about all these categories, two categories, bicategories, abstractions of abstractions of abstractions, right? But of course, by popular demand, everybody wants to hear about monads. Every programmer wants to understand what a monad is. And of course, so in any category theory lecture for programmers has to explain what a monad is, right? And a monad is really, I don't understand why there is so much fuss about monads, because monads are such a simple concept. So I thought a lot about this. Why do people have problems with monads? And I think the problem is because it's the wrong approach to explaining what a monad is. And I thought, okay, suppose that you want to explain what a function is. Okay, it's like you go to a tropical island, you know, and there are friendly natives, and they want to learn functional programming from you, right? Because they've heard that you're a functional programmer, and they ask you, well, what is a function, right? And you try to explain what a function is, and you give them example. You know, like you can have a function that takes a list of fishermen and orders them by the number of fishes they caught. Okay? Or another function takes a person and gives you their age. Okay? Or takes like pre-chewed grain and gives you alcohol, right? And they say, wow, this is some really amazing stuff, right? I mean, it does all of these things and more, right? Function must be like so powerful. We have one thing that like this. It's a kind of mushroom that you eat, right? But this is much more powerful, right? So you realize, okay, so maybe this is not the best approach to explaining what a function is, right? Maybe let's try this. Function is like an animal, right? It has a mouth, right? And it eats input, right? And then produces output on the other side, right? Okay, that's a better analogy, right? But you get into big trouble when then you try to explain function composition. Okay, so what really, why do we use functions, right? I mean, so let's try to really think about it. Why do we need functions at all in programming? And I'm talking about functions in more general sense, also in not only functional programming, but also imperative programming, side effects, whatever, right? I mean, why do we have functions? Can't we just write one big program, right? With all the loops, if statements, expressions, assignments, right? Why do we need functions? So, we really need functions so that we can structure our program, right? We need functions so that we can decompose the program into smaller pieces and recompose it. I mean, this is what we've been talking from the very beginning about in category theory. It's composition, right? And the power of function really is in the dot. That's where the power sits. Dot is the composition operator in Haskell, right? It combines the output of one function with the input to another function, right? It combines two functions, so the output of one goes into the input of the other. So that explains what functions are, really. Functions are about composition. And so is the monad. Okay? So people start by giving examples of monads. You know, there's the state monad, there's exception monad. You know, these are so completely different things. Like, what do exceptions have to do with state? What do they have to do with input-output, right? Well, it's just like with functions. Functions can be used to implement so many different things, right? But really, functions are about composition. And so is the monad. The monad is all about composing stuff. It replaces this dot with the Kleisli arrow. Okay, we talked about the Kleisli arrow, the fish operator, right? It just says, okay, so dot is used for composing these simple functions where the output matches the input. So they're like the most trivial way of composing stuff, right? The fish operator is used to compose these functions whose input type is whose output type is embellished, right? So it's really the output type of a function would be, let's say, b, but now we are embellishing it with some stuff. For instance, the example was with logging, right? By adding a string to it, right? The logging Kleisli arrow. But then, in order to compose these things, we have like unpack the return type before we can send it to the next guy. So actually, like inside the dot, not much is happening. Just one function is called, and the result is passed to another function. Inside the fish, much more is happening, right? Because there is the unpacking, and there is the passing of the argument to the next function, and also, you know, maybe some decision is taken. Like in the case of exceptions, we'll see that actually, you know, once we have this additional step of combining functions, we can make decisions like maybe we don't want to call the next functions at all, right? Maybe we want to bypass them. So a lot of stuff may happen inside the fish, right? And just like we had the identity function here, right? That's an identity with respect to the dot. Right here we had this Kleisli arrow that represented identity that returned this embellished result, but of the same type, right? And that was we called it return in Haskell. And it's called return because it's at some point you want to be able to program like an imperative programmer. It's not that imperative programming is bad, right? Imperative programming could be good as long as it's well controlled. And the monad lets you do programming that's kind of imperative style. You don't have to do this, but sometimes it just is easier to understand your code when you write it in imperative style, even though it's immediately translated into this style of composing functions, right? So this is just for our convenience. We want to be able to write something that looks more imperative, but behind the scenes, it is still function composition upon function composition. So, just like these things form a category, right? This is the category of functions that use composition and identity. That's our category of types and functions in Haskell. Similarly, these guys form a category. That's the Kleisli category, right? So, there are several ways of introducing monads in Haskell, or in any other language for that matter. If you want to introduce monads in, I mean, there are monads in Scala, there are monads in languages. You can define monads in C++. And this way, using a Kleisli arrow, or the fish, is probably not the most popular, because using the Kleisli arrow is like equivalent of programming using the dot, right? I mean, we don't see many programs, even in Haskell, that are written using dots, right? This is called point freestyle, right? Where you just compose function after function after functions, and you never mention the arguments of these functions, right? They are hidden. They are not given any names. They just go straight from output of one function to the input of another function, right? The point freestyle is popular with some people, but it's in general considered hard to read. Right? It's like you really have to look at this and think quite a bit, and finally you get the aha moment, right? And it's great. I mean, the aha moment is great, and you think, wow, that person who wrote this was so clever. But they probably started by writing it, line by line, giving names to arguments and giving names to intermediate values and so on, and then they started like slashing and burning, and eventually got to this point freestyle, right? But it's not easy. So if you ask somebody to do all this monadic programming using just the fish operator, that's equivalent to using point freestyle, and it's hard. And it's not very readable, it's hard. So this definition of a monad with the fish operator is not the main definition that's used in other languages. And I'll show you why, how to get from one definition to another very, very easily. And I will call this next segment fish anatomy. Okay, we'll be dissecting the fish operator. So the fish operator right? The signature of the fish operator is it takes a function from A to MB. Okay, so B is type, A is type, M is this embellishment. And I already mentioned that this embellishment is a functor, usually, right? Well, in fact, in an Kleisli category, this is a functor. So the Kleisli category is built using a functor. We call this functor M in this case because it's really, we'll see, it's a monad, right? So we'll call it M. But it's a functor. It acts on a type and produces a new type. Right? So it's a type constructor, right? Plus it has F mapping, right? Plus it knows how to lift functions. Okay? So it takes one function like this, and then another function that goes from B to MC, right? And it produces a third function that goes directly from A to MC, right? So notice the mismatch, right? This is MB and this is B. So this fish will have to somehow, one way or another, reach into this functor, extract the B, or B's, or no B's maybe, we don't know, right? And pass it to this function, right? So if we are implementing this guy, well, let me write it in infix notation, right? It takes two arguments. This is our function f, this is our function g, right? So it takes a function f on the left and g on the right, infix. And what can we do? Well, first of all, we have to return a function here, right? A function that takes an a. Okay, so how do you return a function from a function? Well, you have to create this function on the fly, which is using lambda, right? So you'll say lambda a arrow, right? So this is notation in Haskell for lambda functions. This is the argument. I'm using the same letter for the argument as for the type, but you know, I mean, types and elements in Haskell are from different namespaces, so it's okay to use the same. I could have put an X here, but then you wouldn't remember that it's of the type A. So we definitely will have lambda A because we need a function that takes an A and returns MC. Now, once we have A and we have F, right? F is from A to MB. But there's really nothing else that we can do but apply this function, right? Unless this is some really... No, actually, we have to, right? We have to apply this function. There's no other way. This is, remember, this is all polymorphic in A, B, and C, right? A, B, and C are completely arbitrary types. We have to be able to define the fish operator for any type A, B, C. So once you say that this is any type, that means you cannot do anything type specific, which means you cannot do anything, right? Except you have a function here that takes an A. That's like your only chance to do something with A. Well, apply F to A, right? So obviously we will apply F to A. Okay? We have no choice, right? And so what the result of applying F to A is something of type MB, right? So this will produce something of the type MB, and I'll name this variable MB without space, okay? So I like naming my values using the names of types, right? So this is my variable MB. So the syntax for this is let MB equals FA. That's like defining a local variable in other languages. In Haskell, this means just giving a name. It's called binding a name to some value. So the let expression is let something equals something in, and here we use this. I mean, it makes sense to use it, otherwise we wouldn't be writing this let, right? So we use it, and this is what will be produced by this fish operator. Whatever is here will be. So 3 dots here, okay? So what goes here? Well, we have MB at our disposal, and we have still untouched G. We have these 2 things, right? And what we want to produce, since this is a function that takes an A, it's supposed to produce MC. So we want to produce MC, okay? So we need a way of taking MB and the G and to produce MC. Okay. So let's introduce something that does this. So this would be something that has a type. MB is of the type MB with a space, right? N acting on a functor, N acting on B. G is of this type BMC, and we want to produce MC, M space C. Okay? So if we have something like this, and we'll call this function bind. Okay? And in fact, let's make it an operator, a binary operator. Okay? So now here we can put our NB, the binary operator, the bind operator, right? The G, and this will not produce now MC, right? And we are done. Okay? So I mean, we haven't done anything because we still have to implement this guy, the bind, right? But we have like eliminated some of the boilerplate. We said, okay, instead of every time when we are defining the fish operator, write this and F acting on A and blah blah blah, it's enough to just implement this guy once and for all, right? And the fish can be expressed in terms of this, right? So we have sort of simplified the problem. I don't know if this is simplification or not. I mean, you know, I mean, this interface here is the signature is kind of very symmetric, nice symmetric, and has meaning, right? It looks very much like function composition. This is not so much, okay? This sort of looks maybe like a little bit like fmap, right? Like applying this function to this, well, maybe flip to fmap, right? But okay, we can live with that. So a lot of people will start by saying a monad is something that has this bind operator, and then you are asking yourself, well, whoever came up with this weird, you know, signature, right? And it's not really weird, it comes from this. Okay. So this is how a monad is defined in Haskell. In Haskell, a monad is defined as class monad M, where, okay, so M here is really a type constructor, remember, right? M is a type constructor, although you don't see it here, but you will see it when immediately when I define the members. And the member is bind. So we have to have bind defined from, well, now we can rename it MA, A and B, and B, right? So that's the signature of bind. If it doesn't fit in this screen, then we can get this. And of course we still have this return that I erased, right? But we still have this identity Kleisliero return that takes an A and returns an MA. Right? And that was our Kleisliero that served as an identity for the composition of Kleislieros. But now we know that we can recreate the composition of Kleislieros using bind anytime we want to, but we still need our identity to make it into Kleisliero. Okay, so I could stop here and say this is the definition of a monad in Haskell, but really this is not what most mathematicians use as the definition of a monad. Mathematicians go deeper into the fish. Okay, they dissect the internal organs of the fish as well, and they say, okay, bind. How would we implement this bind? Well, remember I said before that this M is a functor, right? I never used this fact that it's a functor. And in fact, if I define monad in this way, it automatically is a functor. I can define fmap using bind and return. So I don't really have to say M is a functor because it follows from this definition. So bind is more powerful than the Kleisliero. Actually, the Kleisliero also, if you only assume Kleisliero, you'll also get functoriality from it. But suppose that we know that M is a functor and we want to use it. Well, then how can we implement our bind? Okay. Well, let me again write it in infix notation. So we will have something of MB without space. Oh, well, okay. Let me just say MA. Okay. I will do renaming on the fly. This is very dangerous. Okay, don't do it at home. Renaming variables on the fly usually ends up making you make mistakes. But since you are watching, yeah, you correct me. So MA is bound to a function, let's call it f. So this is our function f, this is our MA, and the function f goes from A to MB, okay? Again, renaming. Okay, so we have these two things. And now I know that M is a functor. So if it's a functor, then I could apply this function to MA, right? Because functor lets me get inside the functor, right? I can F map. Aha! So I could F map F over MA. I could, right? So the signature of F, well, I write the signature separately here so that we know. The signature of F is A into MB, and the signature of MA is MA, right? So this is my function, and I can get with this function under the M here, acting on this A, which will turn this A into MB. So I will get something from this, I will get something that's MB. Aha. So yes, I can do this, but I get not exactly what I wanted, because I wanted to get, oh yeah, let me rename this stuff here. That will be, okay, A, B, B, right? I want to get an MB, not MMB. And again, okay, but if I had a function that can do this, then I could use it. So I would need a function that does this. It turns M, MA, now I'm renaming on the fly, to MA, right? It just strips one layer of functoriality. So it's like if you think of a functor as, remember, as a container, it's like you have a container with a container inside, and you're saying, well, let me just like, you know, turn it into a single container. Instead of container of containers, it's a single container. So this is all an operation on containment rather than on objects sitting inside, and still okay, right? As long as I don't touch the contents, because I don't know how to touch the contents because the contents is polymorphic. Could be any type. I don't know how to operate on any type. So I'll call this function join. And now you see that I can, instead of implementing bind, I can implement join. Once I have join, right? So join would go here. And we'll flatten it, right? Oh, this is why it's called flat mapping in some languages, right? It flattens. It maps using fmap here, and then flattens it using join. Right? Is it called flatten in Scala?
Flat map.
Flat map.
No, but this join itself.
Yeah, flatten.
Flatten. Oh, it's a good name actually, right?
Flatten.
Yeah. Okay. So we are flattening stuff, right? So if you think, for instance, an example of a monad is a list monad. M acting on MA would be a list of lists. You flatten a list of lists, you concatenate all these lists, and you get a single list, right? So in many cases, join is easy to implement. Well, in particular, in the case of list, join is like the simplest thing to implement. Okay, So if we wanted to define, so this is an alternative definition of a monad, you know. But in this case, I have to specifically say that M is a functor. Which is actually a nice thing, right? That I have to explicitly specify it. Monad M, monad M, where, and I can say just join M, MA to MA, and return, but without any change. Return still A to MA. Okay? Sometimes people say this is a lifting of values, right? Like remember in a functor we have lifting of functions. This is like a lifting of values. Take a value A and you lift it to the monadic value. So in case of a list, for instance, you take a value and you make it a singleton list. Okay. So this definition, or the definition with Kleisli arrow, they are not used in Haskell, although they could have been, right? But the Haskell people decided to use this as their basic definition, and then for every monad they separately define join and the Kleisli arrow. So like if you have a monad, you can use join and the Kleisli arrow because they are defined in the library for you, right? So it's always enough to define just bind and fish and join will be automatically defined for you. You don't have to do it. So, okay. But remember, in this case, you really have to assume that it's a functor. So in this way, you know, like the join is like the most basic thing. Using just join and return is really more atomic than using either bind or the Kleisli arrow, because they additionally subsume functoriality, whereas here functoriality is separate, right? Separately it's a functor, and separately we define join and separately return. So at this point I could give you examples of monads, lots of them. Well, not really lots of them, there are like 5 different or 6 examples of monads, the standard monads. There aren't that many that are in popular use, right? And but you can find these things online or in libraries or in books. So, but if I don't give you any examples, then you will be puzzled forever. So let me just give you a few examples, right? So one example. I hope you memorized all this, right? And if not, you can rewind. Okay. So the simple, I think the simplest thing is the maybe, right? So I'll give you an example of the maybe monad, and maybe I'll give you an example of a statement. But why? I haven't answered the main question. Why? Why are we using these monads? What do they solve? What problem do they solve? Well, okay, I said monads are used to provide composition for Kleisli arrows, right? But why Kleisli arrows? Well, we've seen one example that Kleisli arrow was useful, right? When we created this logging thing, right? So really the magic of the monad is not in what a monad is. Monad is just composition. The magic is, why are these Kleisli arrows so useful? And why do they solve, what kind of problems do they solve, and why? So it turns out, and that was like a big discovery by Eugenio Mocci. He wrote this paper, and then Philip Wadler read his paper and wrote and said, yeah, we can use this in Haskell. Let's implement this in Haskell. And this is how Monad came into Haskell. The idea was that functional programming is, everything is pure function, right? Like purely functional programming, everything is a pure function. And as programmers, we know that pure functions cannot express everything, right? I mean, things have side effects. I mean, there are so many computations in which pure functions don't really do much. Like basic things like input-output is not pure, right? A function that get char, if it returns a character, it returns a different character every time you call it, right? So it's not really a function in the mathematical sense. And there are things like, there are functions that access external variables, that some global state, modify global state, have side effects. Then there are functions that throw exceptions. There are functions that take continuations. There are all kinds of weird things that are not pure functions, and that people in imperative languages, they use them all the time, and they say we cannot program without these things. Come on, guys. If we use pure functions only, then we are just heating the processor and not getting anything done, right? So it turns out, and this is like really a miracle, I would say, that everything that can be computed using non-pure functions, things like state, exceptions, input-output, they can all be converted into pure calculations as long as you replace regular functions with these functions that return embellished results. So all these side effects can be translated into some kind of embellishment of the result of a function. And the function remains a pure function, right? But it produces more than the result. It produces a result that's hidden, embellished, encapsulated in some way, in some weird way, right? So this is the interesting part. You have a computation that normally an imperative programmer would implement as an impure function, right? And the functional programmer comes and says, I can implement this as a pure function. It's just the output type will be a little different. Okay? And it works. And this is still has nothing to do with the monad, right? It just says, impure computations that we do in imperative programming can be transformed into pure computations in functional programming, but they return these embellished results. And where does the monad come in? The monad comes in when we say, okay, but I have these gigantic functions that start with some argument A and produce this embellished result, right? And do I have to just write them in line for 1,000 lines of code to finally produce this result? No, I want to split it into pieces, right? I want to chop it into little pieces. I want to chop a function that produces let's say, side effects into 100 functions that produce side effects, and then combine them, compose them. So this is where monad comes in. The monad says, well, you can take this gigantic computation, pure computation, and split it into smaller pieces, and then when you want to finally compose this stuff, well, then use the monad, right? So this is what the monad does. It just glues together. It lets you split your big computation into smaller computations and glue them together. So one example of something that's usually done using impure functions is functions that are not defined for all arguments, partial functions, right? Partial functions is a function that's not defined for everything. Like, let's say square root is defined only for positive integers. So what do you do when somebody calls square root with a negative integer, right? I mean, the program can blow up. That's one solution, very popular. And the other solution is throw an exception, right? So these are the ways, and a function that throws an exception is not a pure function, right? But we can easily change it into a pure function, right? We just have to return a maybe, right? So if we have a function from A to B that is not really a function because it's partial, we can always turn it into a function from A to maybe B. So when it's not defined, for these values when it's not defined, it will return nothing. And for these values that it's defined, it will return just. Right? So that's it. So that turns impartial computation into a pure function. And now the question is, well, so how do we combine these things? Like if you have two such functions and you want to compose them, right? How do you compose them? Well, you have to use a monad. So we have to define a monad for maybe, right? Maybe, we already know that maybe is a functor, right? So we can say, okay, let's define join for it, right? So join would take maybe of maybe A and return a maybe A. Right? Well, it's very easy to define. Join, let's call it MMA, this variable, MMA, right? No, actually, since this is a sum type, maybe it's a sum type, right? It's either nothing or just, right? So a sum type we pattern match, okay? So there is actually only one pattern that is interesting, and that's just A. You can have nested pattern matching, right? And that will just return just A, right? For anything else, return nothing. Because anything else means that either this is nothing, or this is nothing, or both are nothing. In all these cases, there is nothing to return, really, right? I mean, the value is lost. And this is fine. This is a good definition of join. It doesn't, though, explain very well the cleverness of the maybe monad. That it actually imitates exceptions. So instead of defining join, let me define bind. So bind would take A may be A, right? So as a first argument. So we'll do pattern matching on this maybe, right? So we'll say, let's say nothing. Bind it to some F and just A and bind it to some F, right? And now F it has a signature A to maybe B. That's the signature of F, right? So if we start with nothing, there's really nothing we can apply function F to, right? We have to return nothing. There's just no other way. Now in this case, oh yeah, we can apply F to A. Okay? So we'll just return FA. Does it have the right type? FA? Yeah, right? Because F returns maybe B. F acting on A returns maybe B. We don't even have to put a just here because it's already... Well, it could return nothing. I mean, F could return nothing, but it's fine. Right? It has to just return a maybe. So notice what's happening here. We are shortcutting, short-circuiting, right? We are not calling this function. We are bypassing this function, short-circuiting. Okay? If the first, like now think about how it works with function composition with the fish operator. If the first function failed and produced nothing, then we are not calling the second function, right? That's like exceptions, right? If the first function throws an exception, you don't call the second function. You immediately go to the end of your calculation. So this function f here, it serves like the continuation. This is the rest of the computation. If the first part of the computation fails, abandon the computation. Don't do the second part. And you can't do it because you don't even have an argument for it, right? So you can't. So a monad, the monad composition is really clever here because it lets you do things like short circuit. And for completeness, return, that should be just a trivial lifting of a value of type A, right? So it will produce just A, just encapsulates A. Clever, okay? Something that imperative programmers would do by extending the language to do exceptions, we can just do with nothing. And of course, if we want to pass information about the error, right? Because that often happens that, you know, it's like, okay, an exception usually carries some error message or something, error number, right? And then instead of maybe, we use the either type, either string or value. Right? And so there are more sophisticated ways of implementing exceptions. Like, this is like the simplest, trivial way of implementing exceptions in Haskell using maybe. Okay, and the second example I want to give you is state, because that's something that people have, like, this is the weird thing, right? I mean, you have a function from A to B. Well, it's not a function really, a computation from A to B that accesses some external state S. Okay, so state of type S. So you probably have, like, in imperative programming, you will have some global variable of type S, and this function is either reading from it or modifying, reading and modifying the state, and so on. So it just goes on, you know, and modifies some external state. And obviously it's not a pure function because it has access to external state. So, but it can be easily turned into a function, pure function, as long as we pass the state explicitly, right? It doesn't have to be global. We can say, well, let's turn this function into a comma s and b comma s. Okay? So it takes a pair of a and the state and returns a pair b and state, and the state is already modified, right? Now, does this look like a Kleisli arrow? Not really. Right? Not really. Kleisli arrow should take an a and return an embellished value. And this guy not only modifies the output, which is okay for a Kleisli arrow, but also modifies the input type, right? But now that we know what currying is, it's not a problem, right? Instead of writing a function that takes 2 arguments, man, this is a function that takes 1 argument and returns a function, right? That's what it is, huh? Okay. I mean, I don't need these parentheses, but I want to put the parentheses so that you see that this is a Kleisli arrow. This is a Kleisli arrow. It goes from A to a functor on B, and this functor is called state. Okay. New type state. And it's parameterized by the state type, which we keep fixed, right? And this arbitrary type A, which is the functorial, our polymorphic thingy, right? That we are using. And it's just a function from S to, well, A. Renaming stuff on the fly. Okay? So this is this A. And it's factorial in A, right? Well, do you understand it's factorial in A? Because this is a functor that's, first of all, it's an arrow. An arrow is factorial in the return type. Right? It's not factorial in S, by the way. No. Right? Because it's contravariant in S on this side, covariant on this side. So it's really screwed, right? But in A, it's a covariant functor because it's a combination of a functor that's the what do we call it? The reader functor, right? And the functor that combines the bifunctor, that's the product bifunctor, right? So it's factorial in A. But of course, if you want, you can write an F map for this guy and you'll see easily. Okay. Now I'm not going to implement the bind. Well, I'll just tell you how to implement bind, and I mean you should probably figure it out. I mean, how would you do bind? Well, bind would take a state, right? State, and we would have to produce a function that takes the argument A and produces state of B. So you would apply the first one. You would return a function that takes an A, so lambda A. You know, then inside you would apply this state to a state, right, and get the value, and then call the second function with that value, and then you modified state. Okay. That's an exercise. You can do it at home, or you can look it up in the library. It's pretty straightforward. So I haven't talked about some additional stuff, the monad laws, right? Where do they come from? Well, they come from remember the Kleisli arrow? Kleisli arrow, we defined the fish operator and return, and we said return is really an identity for fish, right? Fish identity. And also that fish has to be associative. So these are additional laws, associativity of the fish and the identity law. Actually left identity, right identity. So there are three laws that have to be satisfied in order to make Kleisli composition into category, right? Kleisli category. We have to have associativity and unit and identity. And I sort of forgot about this for a moment and just went through stuff that can be expressed in Haskell, because these additional laws cannot be expressed in Haskell. They are just identities, right? So these are things that we can use for equational reasoning, for instance, right? But they cannot be checked by the type system. So I could start with these laws for fish, right? And then since we know how to express fish in terms of bind and then in terms of join, you know, there is a way to translate them. It's not easy. It's work, right? So I'm not going to do this. I'm going to jump over it and like go straight into category theory, because in category theory I can derive these laws again from simple principles, and then we can go back to Haskell and write them in Haskell, right? So in category theory, all three definitions are used in category theory, but really everybody uses the one with join, okay? Except that they don't call it join, and they don't call it return, and they don't call it the functor. They don't call it m, they call it t. Okay, so the translation m goes to t. Join goes to mu, and return goes to eta. They use Greek letters. They use Greek letters here, and it makes sense because they use Greek letters for natural transformations, and you will see that these are natural transformations. Okay, so now I will switch notation. I'm going to switch notation to t, mu, and eta. So we already talked about return at some point, right? When I talked about natural transformation, I said that return really is a polymorphic function, right? It's a polymorphic function that goes from a to ma in the old notation, right? But really, since it's a polymorphic function, it's really a natural transformation where this is the identity functor acting on A. So it's really a natural transformation. Sometimes people put a dot over the arrow saying for natural transformation. So it's a natural transformation between two functors, right? And this is a component of this natural transformation for some particular A. So return is a component of the natural transformation from the identity functor to m, right? And since we don't want to use m here, we want to use t, right? So we'll say that eta is a natural transformation from the identity functor to t. Okay? And it means the same thing, except that in Haskell we use it in components. Every natural transformation has components, right? So for a particular A, identity acting on A gives you A, T T acting on A gives you MA. Right? Now what is mu? Mu is also a natural transformation, right? I mean, and where join was going from M, MA to MA. What does it mean? What is MMA? It means we take this functor M, act on A, and then we apply this functor to the result. So this is like double application of a functor. That's just a composition of a functor with itself, right? So this, in mathematical notation, this would be T circle T going to T, a natural transformation, right? Double application of T in components, it will give you this, right? Double application of a functor in components is this. Single application of functor, right? It's a natural transformation, right? So in category theory, we have to say it's a natural transformation. In Haskell, we didn't say it was a natural transformation. Like, nobody mentions naturality condition for this guy or return. Why? Because of polymorphism, because of, right? Because theorems for free. It's automatically natural. Naturality condition is automatic. But in category theory, we have to say it. So T composed with T is usually written simply as T square. Okay? T square means just a composition of T with itself. That's shorthand notation. We sometimes write it T square, sometimes write T circle T. Sometimes people just write it TT. So, a monad is a functor T and two natural transformations. Plus, there have to be some laws for this thing. Otherwise, we wouldn't get, if we try to make a Kleisli category on top of this, we wouldn't get associativity and identity laws. So associativity and identity laws in this case would have to be something. So associativity means you want to do a triple application, right? Because you can associate triple application of a functor either left or right. Right? So if you start with T cubed, which is T applied to T applied to T, then you can write it as, you can write it as T circle. You can write it as T square T, or you can write it as T square, right? It's all the same. It's just a different way of rewriting the same stuff, but it's exactly the same, right? So now we can apply mu to T square, right? To the functor T square. In fact, what I should do is rewrite these things as diagrams, okay? Because then it will become clear. In terms of diagrams, first of all, did I mention that T is an endo functor? I did, right? But it has to be an endo functor, because otherwise we could not form the T square, right? Because if T went from C to D, then we couldn't apply T again, because we are already in D. So it has to be an endo functor. It has to go from C to C, right? So here's category C. Here's the same category C. We can go from C to C using the identity functor, obviously, right? Or we can go from C to C using the functor T. So we have two functors between C and C. A natural transformation maps these functors, right? If you remember from the last, right? So this natural transformation from ID to T is called eta. Now, the other diagram is we can go from C to C using T, and then again using T, C, right? Our notation for this is T squared. So that's just notation. T squared is right, right? This is T after T. So we can go from C to C using T squared, or we can go from C to C using T. And we have a natural transformation here that's called mu. So mu is a natural transformation from T squared to T. Okay? We can only do this for endofunctors. We can form T squared. So this is our eta, this is our mu. Now when I say T cubed, okay, so I have C, and I'm splitting it here into T squared and T. Well, it's actually this one. Okay, so let me write this. This is, no, T squared after T. T squared after T, right? Now, I can apply mu here to get to T, right? And I can just apply identity here, identity natural transformation to get another T, right? And now I have T squared, and I can use mu to get to T, right? So we are doing diagram chasing up, but now it's a two-dimensional diagram chasing because now we are using natural transformations, right? So notice what I did here, okay? If you remember this kind of diagram, this is a horizontal composition of two natural transformations. This is an identity natural transformation, horizontally composed with mu. Right? So I have T squared, you have T. I'm using one natural transformation that's a horizontal composition of identity and mu. I think we call it mu after I. Right? So that's this natural transformation. And this is followed by mu, but this time it's a dot, right? Because this is like vertically composed, this stuff with mu. So we have both here. We have horizontal composition of mu with identity and vertically composed with mu. And we want this to be the same as if we split it this way. T squared here and T here. So this is the same T cubed, right? But now we do mu here and identity here. So we get T, and we get T, which is T squared, and we use mu to go from T squared to T, right? So, erase this already. So we want this to give us the same here, because this is associativity. It says whether we first do it on T squared here or first do T squared here, it should give you the same thing. So this is mu dot identity natural transformation with mu. Okay? Now this stuff usually in a book you will see it written in a different way. You will see it as one diagram for natural transformations. Okay, so for natural transformations that would mean we start from t cube, right? And we use the natural transformation I mu, okay, to get to t squared, or we can do mu I to get to t squared, and then we use mu to get to t, and we get mu to get to t. And this combination should give you the same way as this combination, right? So this is usually how it's written. Actually, not even that. Because the identity natural transformation is usually written by replacing it with the symbol for the functor on which it's acting. So this is natural transformation on t, right? This is it. This is an identity natural transformation on functor t. Should probably write it here everywhere, so that's clear that this is this natural transformation. Okay. So instead of writing it, people simply write t here, and there is no confusion because it's impossible to combine a functor with a natural transformation other than replacing the functor with identity on this functor, identity natural transformation. So this is just notation that mathematicians use. So if you see it anywhere in a plane, you will see mu t mu. And you might ask yourself, well, wait a moment, this is a natural transformation and this is a functor. How can they compose these things? No, this is actually a natural transformation. It's an identity on t. Okay? It's just a piece of notation. Right? So I'm going to erase this. And one final identity, well, two final identities is okay, in diagram, in functor diagram, so this is C, this is C, we can apply the identity functor now, followed by T, and of course this is the same as T, right? Identity followed by T is the same as T. But if we apply natural transformations, we can apply eta to identity and get T. Right? So I'm using eta now. It's a natural transformation between identity functor and T. And here, of course, I can use I, natural identity. Right? And that gives me T. Now I have T squared here, and I can mu it and get T. Right? So I got from T to T. Right? And this is written as a diagram that says, ID T. What order should I write it? Okay, but so probably like this. This is eta. Now this is identity, so it's identity acting on T, so I'm replacing it just with a T, right? And I get T squared, and then I apply mu to it, and I should get T, right? So this is equal to this. That's the triangle identity that just tells you that eta is really an identity here, right? And the same goes on this side. If I start with T ID, so this is right identity, I do T eta, and this is okay. So I get these three laws actually. 1, 2, 3. These are monad laws in terms of mu and eta. And let's take a break now. Okay.